Good day. My name is Kyla Baguio from BSCPE 31, and today we will discuss the evolution of CPU, how it works, and how the evolution of it developed through the years of its existence in regards with the YouTube video that we watch. Before we proceed, we have here the objectives. First, we gonna tackle the four parts of discussion, how CPU evolves over the years of improving it. Next one is to understand the fundamental mechanics of a CPU and trace its technological evolution from four from basic 4-bit processor to modern high-speed architecture. So first is the part one, mechanics of CPU. Think of a CPU not as a genius but as a incredible fast follower of a rules. At its core, every CPU from the 1970s to the one in your pocket works on a loop. To, to truly understand the internal mechanics of a computer, one must stop viewing the central processing unit as genius and instead see it as a incredibly disciplined hyper-fast follower. So these have a cycle which called fetch, decode, execute cycle. A logic loop, it is a logical loop that has remained the fundamental law of computing since the early 1970s. In the first stage, the CPU first fetches a raw binary instruction from the RAM, which serves as the computer's short-term memory. Once retrieved, the second that it will do is to decode. The code unit translates that binary string into a specific electrical path, essentially turning a cryptic code into an actionable command like add these two numbers or move this data to another file. So the last one, the CPU executes the command using the ALU, or what we call arithmetic logic unit, the mathematical engine of the processor. So as you can see here, we have a picture of the Intel 4004 and the latest Intel i9. So in the era of the Intel 4004, processors were only 4-bit, so meaning they could only process small or tiny data at once. If you can imagine trying to read a novel but you only able to see 4 letters at a time. You can visualize why early computing was so constrained at that time. So processing a data is very slow in the use of Intel 4004. Um, Now that it's jumped to 8-bit processors, or just like in our days, like the MOS 6502. So it's the chip that powered the original Nintendo at the time. So that is the brain that can handle that could handle numbers large enough to manage recognizable graphics and the first wave of truly interactive home software. As the industry moved into the late 1970s, the engineer focus shifted from simple calculation to sophisticated from simple organization, a transitions spearheaded by the legendary Intel 8086. So now we are in the part 2, Rise of the X x86. So instead of pointing directly to data, an instructions points to a pointer that tells the CPU where should the data actually is. This is like a vector table used to pick random sentences in a program. This chip effectively like a grandfather of the x86 architecture that dominates modern PCs today. The primary innovation here wasn't just raw clock speed, but how the CPU managed its messiness of data. The 8086 introduced a more complex use of the stack, which operates on a LIFO, or what we know last in, first out principle. It is a principle that much like a physical stack of cafeteria trays where the last one placed on top is the first one to remove. This allowed for the birth of the ability for a CPU to pause or subroutines. This is the ability for a CPU to pause a main program, jump into a mini program to handle a specific task, and then back to its exact previous location without losing its place. Coupled with indirect addressing, a system where the CPU looks at one memory location only to find the address of where the actual data is hidden. Software was finally able to become truly complex and modular. This era was epitomized by the Alter 8800. So we have here the um, sample image of the Alter 8800 computer. It is a significant machine that lacked a screen or keyboard, but proved that a microcomputer could be affordable for hobbyists or people who usually use computers. It was his specific machine that inspired the creation of Microsoft, as like Bill Gates and Paul Allen realized that these new and organized processors needed a high level language like BASIC to unlock their potential. So we have here also a comparison based on the video that we watched, the ARM versus x86. So this shows why x86 still matters in an ARM dominated future. So it's just a simple comparison between the two. So it shows here that ARM is power efficient, cost effective, and mobile usage. What it means in mobile usage, ARM can also use in Windows usage or Windows support, but it is more complex in mobile usage compared to x86 that it is high-end performance, so it can um, process a data, more complex data compared to ARM. It is software compatibility and more complex to use in window type support. So next one is the origin of modern operating systems. When we understand the market size, it is important for us. In the US, there are about 32 million small businesses. We're aiming at industries like technology, e-commerce, and professional services, which are about 30% of all small businesses. That means we are looking at around 9.6 million potential customers. The goal is to get about 5% of them. which would be roughly 480,000 businesses. This helps us know who to target and plan our growth strategy. So we have here a examples of picture the IBM 360 or 360, which is commonly used back at that time. So by the mark of computer history, the mid 1980s, the challenge changed again. Computers needed to handle computers with multiple tasks simultaneously without collapsing under the weight of their own complexity. This led to the development of protected mode. So as the time goes by, there's more evolved in the data that a computer need to handle. So it needs to handle more complex data. So the engineers come up with the idea to improve again the CPU and the compatibility of it in working in a more complex um, processor or data. In chips like 8286 and 8386, before this, in real mode, a single bug in one program could accidentally overwrite the memory of another program or even the operating system, causing a total system crash. Protected mode function as a digital fence or protection, isolating different programs into their own memory lanes so they couldn't interfere with one another. This period also saw the perfection of interrupt, a mechanism that allows the CPU to be interrupted by an external event. For example, like a mouse click or a packet of data arriving from a network. Much like, for example, you are reading a book and then someone called you from the phone. So you will put a bookmark in a book that you are reading so that you will not lose the page you are currently in. Then you can answer the ringing phone and then go back again to your book to continue your reading. The CPU saves its current state, handles the urgent input, and that returns to its page in a fraction of a millisecond. This seamless switching is what prevents a computer from feeling frozen while it performs heavy calculations in the background, making the modern multitasking graphical user interface possible. And the last one is a part 4 where they discuss the 32-bit processor. So finally, we reached the high performance era of 32-bit computing, where the goal was to eliminate idling time and maximize throughput data. So engineers realized that while CPUs were becoming lightning fast, the RAM was lagging behind. Because of this, it creates a scenarios where the CPU sat idle waiting for data to arrive because CPU can work now more complex but only has a slow RAM. So even though it can work on more complex processing data, it will just um wait or what we called idle for the meantime because it's waiting for the RAM to load. So to fix this, The engineer implemented pipelining and cache. Pipelining works like a industrial assembly line. Instead of waiting for one instruction to finish the entire fetch, decode, execute cycle before starting the next data or the next process, the CPU keeps multiple instructions moving through different stages of the line at a time or simultaneously, fetching the third instruction while decoding the second and executing the first. To solve the RAM delay, they added cache. It is a tiny pools of expensive and super fast memory built directly onto the CPU. This holds the data the CPU uses most frequently, ensuring it doesn't have to leave the chip to talk to the slower RAM. This massive increase in efficiency and more driven. So we have here a picture or image sample of Microsoft Word, which is released in 1983, also known as MS-DOS, or originally known as Multi-Tool World. Microsoft Word began in 1981 when Microsoft hired Charles Simonyi, the creator of Bravo. The first what you see is what you get word processor from the company Xerox PARSI in 1974. With Richard Brody, with the help of him, they developed Multi-Tool World, or also known as the Microsoft Word. It releases the MS-DOS released in 1983, as shown here in our presentation, as Word 1.0 with tiny space of 150 KB. It can do the mouse enabled or mouse enabling, bundled free with PC World, but basic compared to WordStar. Modern versions demand gigabytes, driving 1980s and 90s software bloat and processor needs. So, as we learned from the YouTube videos that we watch, a system is not only stick on its version as they develop it. As the time goes by, they make engineers always make a new version for it to adapt to the continuously improving technology, especially in our era. That's all for our video presentation.